In Thrust 2, we do research on batteries and fuel cells. Batteries and fuel cells at their heart are very similar types of systems. One is an energy storage system, the battery. One's an energy conversion system, the fuel cell. At the heart of these systems are a little bit of a sandwich of two electrodes, two sets of materials surrounding an electrolyte, which can be liquid or solid or a polymer. Generally, we focus on the polymer side of things, and so in the battery we have a separator that's often loaded with liquid, or there are lithium polymer batteries or whatnot. In the fuel cell, we have a polymer electrolyte that carries protons from anode to cathode. To develop these materials, we've assembled a team in Thrust 2 that is evolving in terms of the way we interact in many respects. And that stems right from the research. There's two different types of redox flow battery work going on. One is to actually design a new chemistry that has unique properties such as high energy output per weight. And the second is to develop components of these batteries. Fuel cell materials is probably our broadest area of application, ranging from work on developing new polymer electrolyte materials to developing new electrodes. Vanderbilt work in particular uses a very interesting and unique way of processing materials for fuel cell membranes. Electrocatalysis work is mostly focused on fuel cells. We do extensive work throughout the team, and it's very collaborative in this particular area. People in the chemistry department and chemical engineering here at University of Tennessee, Knoxville, are studying so-called non-precious metal catalysts, that is, catalysts that have no platinum in them for fuel cells. And researchers at Tennessee Tech collaborate with people at Vanderbilt, and we're involved in that collaboration too, to study different types of non-precious metal catalysts, but in this case particularly aimed at using unique fuels within the fuel cell, such as formic acid. We here at University of Tennessee Knoxville are developing some new chemistry for lithium batteries, or to be more specific, very high, very long range potential type of battery called a lithium air battery. We're developing air electrodes that can work in a way compatible with a lithium battery. Normally a lithium battery would burn up or explode if you exposed it to water, and so very specific materials have to be developed. Each investigator kind of has his own starting point. But now what we're doing is we're swapping materials and putting them into each other's cells, testing them to try to develop more collaborative field. By working as a team, we start to give people access to capabilities that they otherwise don't have. In addition, we give their students a look at, a sort of a different level of research in a lot of cases. So we try to feed the people as well as the materials across the team. This is how we grow, and then the next steps are after we start exchanging people, to start working with the other thrusts and finding intermediate areas where we work in things that combine the electrochemistry that's at the core of much of our work with some of the photo-oriented or nanomaterial-oriented aspects that are central to the other thrusts.